Hi, I'm Tom Rhodes with Duke Energy. My official title is Senior Engineering Technologist because transmission asset management isn't allowed to have scientists. But so they put that in there. Here's the obligatory for Duke Energy. We're a big power company slide. Just so you'll know, when people are talking about a lot of plants, I only work with transmission assets. That's the big giant transformers, not the little pole ones that got power to here. These are a third the size of this room, hold 10,000 gallons of oil, got to have trucks with 36 wheels to transport them, big assets. We got about, all those numbers, we got about 8,000 substations throughout all these 6 states. Some of them were put in the 20s and 30s. Some of them are being built now. So we've got a wide variety of assets to maintain. I'm in the group system intelligence, and we exist to go, hey guys, we got to quit plugging away and look at this differently. All right. I'm part of a group that does health and risk management, asset management stuff, and we had to move it to the cloud. Why do we have to have artificial intelligence to do this? We got lots and lots of data points, but not really enough to be called big data. You know, Audi probably makes more cars in a month than we have major assets we're trying to track. And they'll have millions of points on each car. You know, it's just, so we've got some problems. We're also a regulated utility. O&M versus capital dollars. Where are we allowed to spend money? We're told you can't spend as much O&M. The average lifespan of a big power transformer is a whopping 35 years. Our average fleet age will reach 50 years this year. So we're 15 years over. So that means I got about 4,000 transformers that are more than 50 years old. They're not going to make 70. Some will, but that's a lot of work. So we got to manage how we retire these. Other problem we've got is we've got a lot of guys who've been doing this for a long time. Having guys retire with 40 years at Duke Energy is common. We see 10 or 20 of them every week retire. Big company, a lot of old skills. How are we going to capture that data when they won't let us have apprentices? That apprentice is O&M money. I'm not going to bring in a young electrician or a young engineer and have him follow around that guy that's been doing it for his last 5 years of his career. That's 2 guys doing the work of 1. I can't do that. You know, that's not happening. So we got to find a way to do that. Anybody here need to do more with less? We're at that point right now. I've got 1 engineer who's responsible for 1,000 large power transformers. All right. Here's the standard. Here's what we expect to benefit from using artificial intelligence and putting it in. 9 million people have a version of this slide. It's not real important. All right, we got to analyze our data. Our old ways, we had subject matter experts, engineers, been with the company a long time. They look at it. They've got, each engineer doesn't analyze things the same way. They got their own spreadsheets. Every year, they got to go manually rank, where's my sickest asset to my health, all that stuff. Now, we want to go, hey, let's do it the new way. We want artificial intelligence, machine learning. It can be supervised or unsupervised. People are going, go do this. Well, tried that not too long ago. A different group tried doing the machine learning on big power transformers. So you'll know these big power transformers, they're not made in a factory. They're laid up by hand, every one of them. I can buy 3 transformers exactly the same model, and they will not test the same. Okay, they're massive, handmade. Nobody's making machinery to move 50 tons of copper. It's, you know, there's just not enough of them to warrant it. Okay, so we had the engineers, hey, we tried that machine learning. It doesn't work on transformers. Talking to the great machine learning people, guys at C3, We're going, hey, this is important in predicting failures from our guys who are experts, and they're going, you say that's important. We can't use it to predict failures. That's, it's not linear. It doesn't work. What we found is early attempts, we got limited and bad data. All right, I've got transformer data that we've been collecting for 85, 90 years. 20 or 30 different databases have changed and remodeled and changed from paper systems. It's not all entered the same way. It's not consistent, period. Right down to the bank number. I've got transformer that's bank 1. Bank 1 can be entered as bank number 1, bank space 1, bank 01, BNK 01, 1, 01, number 1, TR1 for transformer 1. They all mean the same thing, okay? Now, tens of thousands of stuff, you got to go in, figure out how to clean that. Oh, and sometimes that 1 is part of bank 11 because I'm at a big power plant, it's got 42 transformers. So you can't, you got to have people who know what they're doing cleaning up data. Okay, we didn't put an investment into cleaning up data. First time they did it, okay? We threw it at IT, said, hey, we can do machine learning. And we go, okay, here's the data. Tell us what you can tell us. It didn't work. It relied on really good IT and machine learning specialists that couldn't spell transformer, okay? I mean, they were really good at what they did, but they didn't know what they were looking at. Didn't know good data from bad data. And most machine learning that we look at is Gaussian in nature, which works great for massive amounts of data, tens to hundreds to millions of data points. Somebody was talking about terabytes of data. I'm going, wow, I can fit all this on a 30 meg hard drive. We don't have terabytes of data, okay? Also, if you're looking at a big transformer, has anybody here heard of a thing called a bathtub curve for failure modes? Okay, throw it away. Only works in 1 in 7 asset types, and it does not work for big transformers, which is what we did. It doesn't work for a lot of big major assets. It doesn't work for the plant. It works for little parts. So we got a lot of nonlinear data, but we want the AI to figure out what we're missing. So we had to figure a way to do that. Okay, let's take a look. We have a lot of engineering analytics. How many of you here have this expert who's got a spreadsheet that he owns? It's his, you ain't touching it. He'll give you a PDF copy if you're really nice, but you're not seeing it. Anybody got any of those kind of engineers or had them? Yeah, okay. Problem is they're good. We got people who've been doing professional engineering, physics-based analysis for a century in our business, okay? They're good. These engineered analytics are good and they're right and they work where they're applied. We don't want to throw those out. Problem is it only analyzes what it's told to look at. What the engineer is looking at is what it analyzes, okay? They're generally not systematic, all right? You saw we had 6 states worth of stuff. The engineers in Indianapolis don't analyze the stuff the same way as the engineer in Florida does, who doesn't look at the stuff the same way as the guy in Wilmington, North Carolina does, who doesn't do it the same way as the guy in the mountains in Asheville does, or that guy on the other side of the same mountains in Cincinnati, Ohio. Okay, they've all got different stuff they think is important, and none of them are wrong. So there wasn't a systematic approach to looking at any of this stuff. Examples of that kind of data, if you're familiar with power industry, would be double Frank scores. EPRI, that's the Electric Power Research Institute. They've come up with an entire Meisen engine, which is an expert engine that's computer-based, that's huge. They've been working on it for 25 years, produces some excellent results. There's a company called TOA. They do dissolved gas analysis of transformers. And they've been doing it for 40 years. They get some really good scoring based on real-world data. There's a thing called the Duval triangle that everybody uses that tells you what temperature your faults are in your company's engineer spreadsheets. So this is good. Problem is it's not perfect. Otherwise, nobody would be saying, why don't we go get an AI solution? Now, AI solutions, you got two basic kinds. You got the unsupervised learning where you feed it a gazillion pieces of data. You run algorithms on it and it clusters it. And then you go look at the clusters and say, yeah, this makes sense, and you put it out. Works really great if you got, a terabyte of data. Okay? Other kind, you got supervised machine learning. It needs a big amount of data, not as much as unsupervised. You got to have a bunch of data that you know is good. Hey, these things failed. We know why. We know here's all the data that led up to when it failed. So you train it with known data, and then you go run it against the whole database, and you double check it, and it works. And you get SMEs to go look at all the features that your machine learning developed. And we can do this in the cloud, okay? I couldn't do this. I've been working with asset management software since the early 80s. We had reports that we were trying to run. We'd literally have to tell everybody, get off the system for 2 days. The month-end reports take 2.5 days to run. And we'd cripple it. Call up Oracle, and they go, yeah, everything you're doing is technically right, but there isn't a machine in the world that can handle that kind of hashed indexing. Couldn't do it. Hey, we can do it now. It's great. So this is the most common type of machine learning I've heard about so far, because you can do it with what you've got. All right, what works? These engineering analytics, they work. AI, machine learning, subject matter expert analysis, guys spending a week looking at the data saying this is the sickest thing I got. All of that worked. Problem is how do I get the most out of all of those tools within a limitation? I don't have enough people. We've got 1/10 the number of engineers working that we used to have. We got 1/4 the number of actual techs in the field fixing stuff. Okay, I don't have as much money as I used to have. Okay, and all of my data isn't perfect and isn't consistent and normalized. How am I going to do this? Okay, we normalize in data. Data governance. How many here have heard about and talked about data governance? All right, we got a few. You need to be talking about data governance. You got to make sure your data is right, and then you got to make sure it's right again next Tuesday, because it's not the same data as it was today. Okay? And if you don't, you go spend the time, you go clean up all your data. Next Tuesday, your data is corrupt again. That needs to be a constant process. You need your SMEs, whether they're IT machine learning experts, you need them, but you also need the guy that knows when he puts his hand on that gearbox, he goes, whoa, something's wrong, boss. You need those guys. And you got to get their input and go over this over and over and over again. It's not a one and done deal. You got to get all of your data into one place. That's where the cloud comes in. Because you're not going to get all of your data in one place if you don't put it in the cloud. It's just, not only is it too much, it's one of the few places where you can talk about all different kinds of data and make it all talk to each other. Now, what we did, we're going to combine analytic methods into a unified process, doing something a little bit different. Okay, what we're doing is a hybrid. We're taking engineered analytics, where we take raw data, run it through those spreadsheets the guys have that we've put into algorithms. That's all the spreadsheet formulas are. We've got a product of them, and we go, okay, guys, are these calculations matching your spreadsheet? Are you happy with them? Is this telling you what you want? Then we put that data into production. Then we go into our machine learning, okay, in our case, supervised machine learning, and we don't feed it just the raw data and they say, yeah, this is good and bad. We also feed it the results of those engineering analytics. So if I've got this super whiz-bang PTX tool from EPRI that does 1 million calculations and it ranks things, even though it's a non-linear ranking because it's looking at 5,000 calculations, but I got it and I got it to rank it 1 to 5 for me. Even though the original data wasn't linear. I've now got a linear ranking. And I take the data from another expert thing and we rank it. And we take the data from a third in our case, hundreds. We look at all these engineering things and say, okay, guys, you got to figure a way to get this on a score. And we used 1 to 5 because we're engineers, and that's what we like, okay? 1 to 10 is too big, and 1, 2, 3 is not enough, so we're engineers. And why it's a 1 or a 2 or a 4 or a 5, the answer is, if you got anybody here talk to an engineer, the answer is, it depends, all right? Because I can tell you right now, we got transformers out there. One of the gases we look at is a gas called ethylene. It doesn't get created until you got 700 degrees C, not Fahrenheit, of heat. That's when that gas starts forming from thick insulating oil. I got transformers out there with 400 parts per million of ethylene that I'm going, I don't care. And I got another transformer that it got up to 40 and I'm going, oh crap, take it out of service, it's gonna blow up. Okay, and the reason is the one with the 400, well, it started making that ethylene the day we bought it, and it's made about 5 parts per million of ethylene every day for 40 years. Don't care. That one that's got the 40, yeah, it's 30 years old, and it's never had a part per million in its whole life. So that 40 is like 4 orders of magnitude bigger than what it had before. Well, that 400 on another one is less than 0.1% change. And a Gaussian thing won't pick that up. It'll say you reach this point. It may look at the rate and and they're really sophisticated, but that's the kind of stuff we're feeding in there. Now we feed the same raw data into it and we run it. And then we have the subject matter experts come in and they go, well, that's BS, throw it out for all the features. Then we get a final product. People are talking about predictive analytics and they haven't been very good. We're now running in the high 80%. I can say that thing's going to fail within 2 years. And it matches what all the engineers are thinking too. So it's not just the machine says it. The engineers go, oh, all right. So we want to get a good risk score so we can do this. Now our problem is this system is never going to have everything. It doesn't make the decision. It's in the cloud. Nothing is automatically triggered by it, but it tells the subject matter experts, here's where you need to look. And it's working. So when we go to analyze risk, we got 300 engineered analytics just on transformers. I think we got 250 on circuit breakers, got 104 on a thing called a load tap changer. We got over 5,000 machine learning features that look at all that stuff. Got to have the cloud to get all that and get it organized across 6 states all the way around the world. We look at performance, the asset health, inspection data, attributes, historic data, electrical test data, oil test data, temperature data, online monitoring data, laboratory data. How important is that transformer? How important is this thing to public safety? I got 15,000 gallons of oil. Well, if that 15,000 gallons of oil is 50 feet from the Anclote River, which is just over here, Tarpon Springs, if I dump 10,000 gallons of oil, because that thing springs a leak and it dumps into a pristine waterway that goes to where all the sponge divers dive for sponges, that might be a bigger issue than if that 15,000 gallons of oil is sitting on a place that's got a concrete dump over here for it in the middle of, northern Florida woods with nothing but acres of sand and pine trees around it, okay? So we look at everything from the environment to the economic impact. I lose a transformer and 50 people's houses go out. I lose a transformer and the hospital's without power and on the generator. Not so good. Or that transformer there goes, it's no different than if one 40 miles away goes, but that one is within view of the airport and is on the busiest road in the city of Largo. That goes up in a fireball. Guess what? We're on TV. People at the airport have nothing to do, so they send the airport fire trucks to shoot foam at it. You ever try to clean all the foam off the substation? If it was out in the middle of the woods where we wouldn't care, we'd have said, let her burn. Safest, cleanest way to take care of it. Yeah, I know it sounds ugly, but the amount of man dollars and hours and everything spent makes a difference. So all of those things go into health. What's the probability this thing's going to die? Criticality, what happens if it dies? Does our reputation get hurt? Or does it cause environmental damage or people without power? Okay, this is a concept slide. I'm going to go through and throw the whole thing up real quick. There we go. We got power transformer circuit breakers. We got online monitors. We got a Maximo database, a Doble Web database, TOA, our DOMs and TOMs. That's our transformer outage management system and the distribution outage management systems. AFS is our asset failure system. That's where we keep track of everything that died. We got a lot of data sources. Okay, and they're all feeding data, and we put them into a data hub and our IT maintains this good data hub. That data we send over C3, and we run our machine learning and our modeling on it. Okay, whether it's all different kinds of data. From that, we get our indexes, our prioritizations, our watch lists, notifications when we need them. Our subject matter experts, we have them say, is this right? And we go back and we say, go change all of that stuff until it makes the SMEs happy. The SMEs were involved in creating the analytics that we use, that were from their spreadsheets that they were guarding, and we had to threaten them with death to get them out of their. No, you need to do it. That's on my home computer. You can't. What do you know? So basically, that's the overview. We got a firewall that keeps it out. Now, power companies, NERC, SIP, we got some really stringent regulations on what you're allowed to be able to do over the internet. Our application feeds data to the cloud, provides reports and analytics and all kinds of indexes and tools that we can use. It doesn't make a decision. Never will a work order be created or a transformer turned off or a line turned off ever from this application. All it does is say, look here. Okay, it's the smartest smoke detector in the world. It smells the smoke and said they didn't put enough salt on that grilled cheese before they burned it. Okay, I'm going to give you an example. This project is right at the halfway point for doing that big of data. We've gotten half the company done. Okay, when we were rolling out one of our regions, we're coming up there and there's a transformer that I know the subject matter expert engineer. We need to get this replaced. It was on a replacement list. We need it done in 2019. Okay? Only thing is this is a $2.5 million to buy it, $2 million to install it. Mammoth thing, you got to get clearances to drive it down the road. Big project for us. Operations and finance people said, if we don't do this one, we push it out to 2023, we can do these other projects instead. And they go do that. And then I'm rolling out HRM and I go put it up and I say, hey guys, yeah, this is the next one that's going to fail according to this. There is a 65% chance that it will be dead within 2 years. I got $100 that says it ain't going to make it 2 years. And I had two management people get up and go, uh-oh. Because the day before was the day that they had pushed the project out 5. It was already, it's getting done next month. But the data matches what our people see. So not only did this change us doing something smart, not only did this change how that asset got looked at, it's changing the entire process. Now, when the people in operations and the finance people say, we want to rearrange these projects, they go look at, what's going to die next and what's the health and how critical is it? they have all these fancy criticality scores, and they say, well, what are you using? And we fed them ours, and they go, oh, wow, that's really good. Can we use that? Okay. So it's also sparked a review of how criticality is calculated. You got to know data that, well, we were taking guesses because they didn't know. All these people are now looking at these, okay? We're done with half the fleet. I now got the other half of the fleet saying, I need that data this month. And I'm going, I can't clean up all the bad nameplate data on 5,000 transformers this month. Well, what if we get more people to do it? And I go, those guys cost $400 an hour. I can't have an intern come in and clean up data. They don't know what they're looking at. And they're going, oh, we had this big, long project, good project plan. We're meeting the schedule. I think we're a month behind after 2.5 years, which isn't bad for us. And they want it now. All of a sudden, we're good enough to where they want it now. That's a nice problem to have. All right, another one. We're now taking risks. I got a transformer I know is going to die in the next 2 years. Not a big deal. It's anybody know anything about transformers? There's 3 phases in transmission power. Sometimes we have one transformer that does all 3. Other times we have 3 transformers that do 1 phase each. In this case, it's one of 3 transformers that do 1 phase each. And we got a 4th one identical to it sitting there. So if one dies, we can just put the other one in quickly. That's great. Problem is that spare is also the spare for where we use the spare up 10 miles down the road. And we can change that spare out in about 4 hours if we need it. And the budget says the new spare for the other substation isn't going to be in for 2 years. All right, we're going to run this one to failure. We're going to take a risk. We can have it done in 5 hours. But if we do it in 5 hours, then there's no spare for the other sub or this sub. They're all gone. And then if another one goes, So we're taking a calculated risk. Not a high-risk area. It's a semi-rural part of the country. A 5-hour outage happens with bad windstorms when trees take out power lines. So we're managing risk. We're not saying we're not taking no risk. We know this transformer ain't going to make it. We're hoping it makes it till another spare comes in for the other site so that we still have at least one spare for these 6 transformers. 3 here, 3 there. So what we're doing is we're not, hey, this says something's bad. What are we doing? Nothing. Of course, we're doing nothing calculated, knowing our risk, knowing our criticality, knowing what we can do, knowing the location. That kind of decision couldn't even be talked about. It's whoever has the most political clout would get what work they had to be done. So this is working. All right. So we're running this to failure, and we're increasing DGA frequency. That's dissolved gas analysis. That's where we measure the fault products of thermal degradation of paper or oil in a transformer. We're going to go say, is this thing degrading faster? If it is, we may change our mind. So we're monitoring it a little bit more. But we were able to make an intelligent decision because we had enough data to do it. Now, saving time. 2 years ago, they say, hey, I need you to tell me what 15 transformers we're going to replace next year. That's in the budget. We want to proactively do 15 in all 4 regions of the company. That's a great deal to do. Now we have a problem. That SME has got 1,000 transformers, and he goes and gets all of his data, and he starts looking. 6 weeks later, he gives the boss a list of 15. Looking at all of his test data, all of his work order data, all of everything he can get to, and not, being able to rank everything because he's got to go through. He doesn't know what changes happened in the whole system. He's got to go through every test system and go see where were changes, what happened, how did stuff happen. All right? There were a lot of tools he had to make that better. I mean, at least he could do it. Okay? Other region, it was a 3-week process, not 6-week, but that guy only has 500 transformers. Okay? Those 2 regions now have this. The one region took 3 days, the other one took a little less than a week. So I got an engineer from doing nothing but working on a project for 6 weeks to where he's done in a week. And now that they're looking at it, he's going, And what the system did is it says, all right, I'm going to take all of your data and I'm going to say, here's your worst. And he'd go look at the top 50, and out of that top 50, he easily pulled the 15 he knew were worst. Okay? It made it to where he didn't have to do a whole fleet analysis by himself with spreadsheets, with data from 14 or 15 different systems. Some of it, no, you can't have that data. You don't have the IT access. All kinds of stuff. So a cloud-based machine learning, artificial intelligence system, problem is those guys are salaried. What good saving weeks of time for those guys? They can be working on more productive stuff like fixing the analytics. All right. Here's some lessons we've learned, okay? We've learned that a hybrid model, when you have finite data, not massive amount, but you do have good engineering and physics-based analytics, and you do have good data that you can get to, it's accurate in ranking and predicting failures. We've had stuff it said, hey, this is going to fail, and when they went look, got there just in time. And then we've had other stuff, how come you didn't catch that? I got 25 worse than that, boss. So it's not perfect, but it is predictive and accurate enough to trust. Okay, data cleanup and maintenance is essential. To get this rolled out, we spent 80% of our effort for the first 2 years cleaning up data. That's all we did. We got more improvement in results, even from our existing systems, just by doing that. Going forward on the team, we've got more people cleaning up data, permanently hired. That's their job. Maintain and clean up data. If they have any spare time, they get to write a report. That's the whole job, because that much data, it's not all in one plant. Literally have a guy go, man, we don't know what this is. The paperwork for that transformer got burned up 30 years ago. It's a 70-year-old transformer. Nate, there's data we need to make decisions we don't know. Have a guy get in a truck, drive to the transformer, and read the nameplate. Okay? So we're still doing data governance. If you're not willing to do that, you do a one and done, which a few people have had. You put it in a project. There's capital project dollars to clean up the data. The next year, when the project's done, we're not clean. You can't do that. You're going to have to redo your work. Everybody's seen some variation of the little circle, plan, do, act, check, action. Okay? In our world, O&M and capital dollars and how we can spend them are a really big deal. We're not a for-profit company. We're told where we're allowed to make money. I can sometimes get stuff on a capital project, but then next year that project's done. How do I do improvement if I didn't budget to do that? And I've had people, well, that comes out of O&M money. We don't have any more O&M money. And I go, then why are we even starting? And why do you talk about continuous improvement? I had one of our IT guys goes, look, at some point we're going to have to just live with these analytics and use them for a few years. And I go, what part of continuous improvement is saying at some point it's good enough? And we're making those kind of decisions, and that's where we got to do it. Real quick, I'm going to show you a really ugly screen. It doesn't have the pretty fancy graphics, but this screen is hugely meaningful for our engineers and the guys making decisions. I got some stuff blanked out, not supposed to share. This is just the quick operational screen for a transformer. That blue line on the bottom, that's its risk. We call it machine learning risk because we have two scores that they look at heavily. What's our engineering health score? What's our machine learning risk score? Sometimes they agree, great. Other times they go, oh, and we got to go figure out why. Does the machine say this is sick? But the engineering score says it isn't. Something's out of whack. We don't have great data, but that's how we find good data and bad data. So in this case, you can see a few years ago, this is that transformer I was telling you about, by the way, that they went and changed the replacement schedule because, oops, it was running along fine and it was on the replacement schedule, and then that big jump happened in that blue line. But how it got there is not real relevant. And then it's running along and it gets worse, and they're gonna, but that kind of data saying, no, it's getting sicker faster. And if you take a look at the bottom, that red line that's going up angularly, it was dead flat for 25 years. That happens to be how much energy caused by a fault in the winding paper, which is what keeps transformers from shorting out, we're creating. The squiggly red lines are load. Those other colored lines are PTX analytic indexes. And they've got system cooling scores, system program scores, cooling scores, oil health scores, double power factor scores. Do we have a ton of open work orders? What's the LTC's health, the bushing's health? How critical is it to us? This one's pretty high. Got some safety scores on there. What's the percent flammability of the stuff? In this case, it's 0. Okay, I'm not worried about a fireball. But that's so that the guy going out there to work knows, okay, there's a lot of oil, it's high voltage. That 4 is pretty high voltage. In this case, we're looking at a 230 kV transformer. So that tells the guy who's looking at it, all right, I need to be thinking about this kind of minimum approach distances and all kinds of fancy stuff. And then we can go look at our oil analysis, our electrical tests, our work order history, our online monitoring. That's CBM, condition-based monitoring. That's where we have temperature monitors, oil monitors, bushing, all kinds of stuff. And then SME comments. So when the SME goes, that's okay, he'll go take and make this thing say it's stable. And he has to add comments. There used to be, if things were good, they just ignored it. They only put comments or said did something if they found a problem. Well, then management go, how do I know you looked at that? Oh, if there's something there, I'd have done something. Well, we're now forcing them to keep track of it. We can actually see what the subject matter said about it. We do monthly health calls on all of our sick transformers and add notes, and anybody can go see that one place. So I'm now getting data from the CBM is 3 or 4 systems, the work order is a couple, all that stuff. It's pretty good. So although that screen isn't real pretty and fancy like some of these dashboards people give you, the guy who's looking at the transformer goes, oh crap, he knows what that means. And that's who my target market is my SMEs. So when the managers ask them, they can say, no boss, here's why. Anybody got any questions for me? Cool.